Hello, welcome to our presentation on advanced AC/DC power architectures for modular data center enclosures. Our technical directors are Mike Bronner and Tyler Balkzoon. I am Adam Silvestri and my teammate is Alexis Noriega. So for a quick company overview, Electric Boat is located in Groton, Connecticut, and they are the design yard and prime contractor for the Virginia-class submarine program. They pride themselves on being defined by their people through their skills and their commitment to the company. So what is data center power distribution? Well, a power distribution system is what delivers power from the input to IT equipment such as data storage and servers through a series of switches, filters, and converters. Some of the most important criteria we considered when designing our system is redundancy, availability, efficiency, power monitoring, cost, and modernization abilities.
What is a mobile data center? Mobile data centers are self-contained enclosures able to be deployed wherever needed. They are modular, portable, and need to be rugged in order to be transported and deal with various temperatures.
So the main motivation for this project is the fact that in the future there's going to be very high power requirements, around 400 volt DC, and most existing data centers today are powered with three-phase AC, with conversions to DC only on an individual component level. So where this project comes in is that we're going to create a flexible, centralized DC system that allows for component upgrades and meets the requirements of around 400 volt DC. On the bottom here, you can see a traditional AC power distribution with conversions on the individual level within the server rack. In this project, we're going to push that conversion further along in the system to make it just overall more efficient.
The economic impact of this project will be that the company will have an improved, cost-effective DC power system for mobile data centers. These data centers will have increased power efficiency and reduced maintenance need. Opportunities to reduce costs and complexities will also be introduced for this system, and potentially reduce overall costs for the company.
Our anticipated best outcome is the identification and assessment of power distribution technology and components for a mobile data center, a model that can provide required power characteristics as well as account for component changes and upgrades, and finally, a prototype development plan to support potential proof of concept demonstration. So we believe that our anticipated best outcome was achieved. We completed technology down selections through Pew matrices that satisfied our identification and assessment of technology. We created a MATLAB model showing the capabilities of our system as well as having descriptions, which was our concept model. We created simulation models showing solid state transfer switching and the speed that this was occurring. And we also made a bit of progress on a physical prototype model, although we were not able to fully test that to the extent that we would have liked.
Our first team key accomplishment was our initial research into power distribution systems and of specific power distribution components, some of which are shown on the right. In our initial research, we became familiar with different power distribution architectures. We also narrowed down important concepts and criteria for our system, and we finally decided on a direct current system, which was in line with our ABO. We then looked into different types of UPS systems, PDU technology, circuit breakers, transfer switches, battery technology, cooling systems, power monitoring, and finally bus systems.
So our next team key accomplishment was the creation of our concept model for our proposed power system. So this was based on our Pew matrices and just our overall technology down selections. You can see an example of one here on the right for our type of circuit breaker technology. And so using these matrices and our other research, we were able to create this system that shows interconnection of components, what type of component, and just overall how everything is connected together. It also includes detailed descriptions and justifications of why we picked each specific area of technology and why we believe it's the best fit for our system. And so along with our TDs as well, we looked through this before finalizing our concept model and we were able to come up with what we thought was the best version of our power distribution system, which you will see in the coming slides. Our third key team accomplishment is our deeper research on solid-state technology. So coming into the second semester, we had done a lot of research on power distribution systems and all the technology within it, and we came across one specific area of solid-state technology that we thought would be a good idea to focus on and use to model and create simulations from. So solid-state circuit breaker consists of semiconductor switches, voltage clamping circuits, as well as control circuits that facilitate the switching process. So why we thought the solid-state technology was so much better than traditional transfer switches and circuit breakers is that it has much faster switching speeds, no physical moving parts, and greatly increased reliability, which are all things that would benefit the type of power distribution system that we are looking to create. This is our completed concept model. As you can see here, we have each step of our system in a subsystem block. Our input circuit breakers, our transfer switch, UPS, our main PDU, and our rack PDU, all shown there, as well as the fiber optic connections back to the power monitoring. And in blue here, you can see what I just talked about in the previous slide. This is kind of where we focused our research and our simulations for the second half of the year, as we thought it would provide us with the most benefit to our project. So a quick summary of my individual accomplishments for the year. The research and analysis of power distribution components for a mobile data center, including technologies such as power monitoring, circuit breaker and solid state technology, PDU technology and its uses. I also completed simulation models of our proposed power system, such as self-learning of Simscape electrical software to actually conduct the simulations on. I modeled circuit breakers and transfer switches using our research solid-state technology. First up on my research focus was power monitoring. So, looking into this, I wanted to learn about power monitoring architecture such as SNMP type communication, which is what you see above, with management information bases and agents that communicate to send data through these fiber optic cables up to our main manager, where this communicates with our user interface, which is how you are able to view and control your system. I also looked into a combination of DCIM, data center infrastructure management, and BMS, building management systems. Those two combined together create a bit of a control and monitoring dual threat, you could say. I also looked into cabling and PDUs quite a bit and what type of PDUs we are going to use. For our system, is going to be switched, basically meaning you have the remote ability to turn on and off switches, look at power draws through the PDU, and have a comprehensive monitoring view of your power distribution unit. Also looked into cabling methods and techniques, as you can see in this diagram above. In our system, our fiber optics as well as our power cables are going to be contained in racks above the enclosures themselves, which saves a lot of space, allowing it to just run along the top of the cabinets rather than taking up more floor space in our small mobile data center. So next up on the focus of my research is circuit breakers and solid state switching. So in this circuit breaker diagram, you can see in the light blue is the solid state circuit breaker being compared to something such as Z-source circuit breakers, current injection, mechanical breakers, and snubbered mechanical breakers. And you can see that the solid state circuit breaker has a much slower turn-off time, much lower rate of failure, and a lot fewer process steps compared to some of these other options. However, it does have quite a bit of loss. The other beneficial factors, though, of a solid state circuit breaker kind of outweighs the higher losses. Next up is the solid state switching. You can see here is a diagram of a three-phase AC solid state transfer switch. You have your three switches, your A, B, C, coming from each source, as well as your control logic and gating signals, which is what actually drives the switch to turn on and off, essentially transferring your voltage from your primary source to your alternate source. I also did a bit of research on the different control methods. I wasn't actually able to implement a completely working control circuit in my simulations, but I was able to get kind of a partial control circuit in my physical simulation. Next up is the simulation portion of this project for me, which is a lot of the second semester I spent doing this. The first actual simulation I completed was on the left here, my single phase AC solid state circuit breaker. So this basically has one single phase AC source sending our voltage through our single switch, which is then being monitored at the load to make sure that the switch correctly turned on and off. And I kind of just use this to troubleshoot the thyristor switching on Simulink just to kind of understand the complete operation. And you can also see at this point I only have a physical signal triggering the switch, no type of monitoring or controlled circuit yet at this point. So then I improved that simulation to a three-phase solid-state circuit breaker, basically repeating that single-phase switch 3 times in parallel to create this three-phase switch. So I use this as a basis for my transfer switch model, which you will see on the next slide. These are some of my most important simulation outcomes. On the left here, you can see my main three-phase AC solid-state transfer switch simulation. This is what I spent quite a bit of time on this semester. You can see on the left in gray, you can see our sensing and control circuits. Those are all partial, not fully completed to the extent that I would have liked. But my main accomplishment on this is that I was able to swap between two three-phase power sources. Not manually this time. It actually has a bit of sensing and control that goes into the switching operation. On the right here, you can see one of those sensing circuits. This circuit essentially monitored magnitude and phase angle of the two sources and made sure that when the sources switched from the primary to the alternative, that everything was within a certain range in order to stop current rush and essentially frying some of your components that are very sensitive down the line. So the waveform you see here is actually the voltage being monitored at the load of the transfer switch on the previous slide. So in the left image, you can see that the primary voltage source begins to experience a bit of a voltage sag in which at about 0.4 seconds, the transfer switch initiates, and then on the right, with a much more zoomed in view, you can see that at 0.4 seconds, that primary source gets driven to 0 while the secondary source is turned on with an extremely fast switching time of around 100 microseconds. Compare that to some traditional automatic transfer switches up in the 10, 20, 30, 40 milliseconds. You'll find that this one has extremely faster switching speeds.
So here again is our power system concept model showing our power coming into a solid state circuit breaker, into a transfer switch, and then into a UPS, PDU, and into a switch PDU, all connected through fiber optics into a software manager to be viewed. Here's an overview of my individual technical accomplishments this year. The research and analysis of power distribution components for a mobile data sensor. This included transfer switches, lens flow power supplies, battery technology, and cooling systems. I also worked on the hardware model for our power system, and this included research into methods of prototype testing, and eventually building a physical prototype to test power quality after a transfer occurred. And for this I used Triax as the main power switching component. Some technology of interest I did some research on are unthrow power supplies and battery technology. For these I looked into the type of power to be used, the configuration of the UPS, and the type of battery to be used, which had to be safe and reliable. I also did some research into transfer switches, where I looked into transfer time and power quality, as well as static and solid state transfer switches, and finally automatic and electromechanical transfer switches. Lastly, I looked into cooling systems, where I took into account safety, efficiency of cooling, and practicability. In my initial planning for a prototype, I created a circuit diagram shown on the right. Here you see two AC sources going to a switch each, and then to a triac. The gates of these triacs are connected to a resistor and a switch. These are used to turn the triacs off or on and to activate them. They are finally connected to one last switch and then to the load. For the prototype, two 115 AC sources will be used to power it. The triacs are used to control the power transfer. The various safety switches included are for testing and measuring the prototype, and the load will be measured with a multimeter. When building the prototype, a perf board was used in order to mount the components. A perf board was used in order to handle the high voltage delivered to a prototype. On the right, you can see the top and bottom of the board showing the components and the connection between each of them. To test the prototype, the power quality will be measured at the load. And to do this, a multimeter will be used to take a measurement of magnitude and phase of the voltage delivered before and after a power switch has occurred. With the results from this, we should be able to see the effectiveness of the components and of the prototype overall. The main goal of our prototype is to test the functionality of the technology used in our power system. With our power system, we will be able to show improvements in transfer time and power quality. And with the results from our prototype, we will show that transfer switches using semiconductor switches and the use of solid-state technology are a key part in improving data center efficiency, as well as advancements in data centers in the future.
Although we did claim that we met our anticipated best outcome, there definitely is a bit of work that could be continued on this project. First up is the extension of simulations to different technologies, such as the entire power path, modeling UPSs and PDUs. The capabilities for this type of simulation is definitely there in Simulink. We could also spend more time building a bigger control circuit. As I mentioned before, we only had a partial control and sensing circuit. We could also test alternative solid-state switch configurations, such as this circuit on the right that has a current commutation ability. The solid-state switch I was able to model was not as complex as something like this, which is why I thought it might be a good idea for future work to explore different architectures. For our prototype, the addition of a microcontroller would be very beneficial to automatically detect fault and switch, as well as just us having the ability to test the circuit and troubleshoot a little more to make sure it all ran smoothly.
Finally, we would like to thank our technical directors, Mike Bronner and Tyler Bobzun, for giving us their guidance and providing us aid throughout our Capstone project. We would also like to thank Mike Smith and Dr. Sunak for additional assistance in the Capstone program.